How to monitor the performance of a light microscope in time. Metrology tutorial for light sources characterization. To obtain reproducible data, the light sources represent one crucial element that can be monitored easily. How to measure the power of an excitation source in light microscopy. How to follow its evolution over time. What is the source stability? How to measure and analyze it. We propose to answer these questions for conventional microscopy setups as wide-field, confocal, and spinning disk microscopes. Warning: the measurements that we present are done on very intense sources of light that can cause irreversible eye damage. They are carried out by professionals trained in laser safety. Be sure to work in accordance with the health and safety standards of your research center. Beware of sources of disturbance. Remember that the optical path of the excitation chain includes various elements that can interfere with the measurement. In order to obtain accurate, reproducible, and interpretable data, it is also necessary to take into account external factors that can affect the power and stability of the illumination. These include fluctuations in equipment and environmental temperature, direct airflow from air conditioning systems, changes in humidity, and instrument vibrations. To ensure comparability and reproducibility, measurements must be carried out under the same environmental conditions between two series of measurements, and with the same optical elements along the route. Conditions to realize a perfect monitoring. Be aware that light sources need time to stabilize, especially gas lasers like argon laser. A change in heating time may be a sign of laser aging. In order to compare your measures, you have to work in the same conditions all the time. Like being always in dark conditions, use the same low magnification objective and the same optical path, including dichroic mirrors and filters. For the measurements, you need a power meter and probes. These measurement tools are available among many others in the Metrologie suitcase, made available by the GT3M of the RTMFM, the French microscopy technological network. Different types of probes exist depending on the power of your source to measure. Two types are often used. The photodiodes are frequently used to measure power range from 50 nanowatts to 500 milliwatts and wavelength in visible range to close infrared. The thermal detectors are dedicated for a strong power source as a femtosecond pulsed laser. The power range can reach more than hundreds of watts, and they cover the full visible and infrared spectrum. In our example, we will use the microscopy slide probe. It is recommended that the power meter and the probes are calibrated at least every 2 years. Some stability measurements require recording values over time. For that, we recommend digital console power meters, like the Thorlabs PM100A, available in the Metrologie suitcase. We'll now show you the 3 types of measurements to be carried out on your systems to effectively characterize the stability of your sources: long-term, short-term, and mid-term monitoring. The protocols can be found in our 2022 paper, Faclaris et al. A similar work can be found on the webpage of the Quarep-Limi group. The aim of the long-term monitoring is to monitor the laser power over the lifetime of the microscope to provide a long-term history of the laser. This can highlight environmental changes of the room, gradual laser aging, and the impact of after-sales interventions on your system. This measure ideally has to be done once a month. Here you can see the graphical representation of 4 laser sources on a confocal microscope. Depending on the nature of the laser, its stability changes over time. Example, the green line for the argon laser source. We can observe the after-sales interventions each time there is a laser peak. The aim of the short-term monitoring is to estimate the possible fluctuations in illumination during fast time-lapse acquisitions during a short time period. We want to validate that the produced image allows a quantitative analysis in intensity of signal for high temporal resolution microscopy as F techniques, for instance, or multidimensional acquisitions as mosaics or Z-stacks. The protocol of measure required the power meter with a data logger to register the data. You need to perform one measurement per second for 5 minutes. The last measurement is the mid-term monitoring. The aim is to measure laser variations over a period of a few hours to highlight any type of direct or indirect fluctuations in laser power. For example, thermal fluctuations in the room, laser alignment micro variations, vibrations, etc. It requires a power meter with a data logger, as you need to perform one measurement every 30 seconds for 2 hours. For short and mid-term monitoring, you ideally have to do it every year or every time you notice something strange with your laser stability or the environmental conditions. The metric we propose to assess the source stability is the stab factor. It is used to weight laser amplitude deviations over time between 0 and 100%. The closer this value is to 100, the more stable the laser is considered to be. A limit value of 97% is experimentally defined. When the stab metric is out of the limit values, several interpretations are possible. In short-term measurements, for example, a gradual rise may indicate that the laser's warm-up time has not yet been reached. A gradual decrease or particular pattern cyclicity may indicate a loss of laser efficiency. On a mid-term measurement, variations can be correlated to thermal variations of the room as shown with the purple curve. We propose to perform the measurements with the 10x objective in position. Ensure it is clean and presents no sign of damage. 1 hour after turning on the system. It is therefore necessary to focus on a sample before positioning the sensor on the sample holder in order to obtain a reproducible measurement. Once the probe is positioned, you can center it with the transmitted light illumination spot. This will assure a good centering of the sensor with objective lens. Before any measurement, identify the excitation wavelength of your laser or light source. For monochromatic laser, you need to indicate the exact wavelength to measure, for instance 488 nanometers for your argon laser. For non-laser source, as LED or lamps, you have to put the wavelength peak value of the excitation filter. To display the measurement correctly on the power meter, we opt for automatic adaptation of the power scale. Proceed by registering the zero reference signal under the dark room conditions. These measurements are valid for any type of fluorescence microscopy, in particular for wide-field confocal or spinning disk. In point scanning confocal, the scanning illumination method induces measurement artifacts due to laser off time between each line and frame. It is therefore recommended to use scanning conditions with as few pixels as possible, or ideally in bleach point mode, in order to define a single spot to be scanned, thus eliminating or reducing as much as possible the laser off time. Let's take the example of a confocal microscope. All you need to do is configure a laser track with 100% power with the fewest pixels to scan, maximum zoom or spot mode, and with the maximum pixel dwell time or lowest frequency. Then run a scan long enough to measure the laser continuously over time. At the same time, the power meter is connected to the computer and the data logger software, configured to the wavelength of interest and set to 0. Then configure to record data at the required measurement interval, depending on whether it's a short time measurement, 1 second interval for 5 minutes, or a mid-time measurement, 30 seconds interval for 2 hours. Other measurements variations are possible based on laser power. For example, the linearity of a laser, and its AOTF, if applicable, can be determined by making punctual power measurements while varying the laser intensity between 0 and 100%. A linear regression fit of the plot can give us the linearity of the laser. It is also possible to measure the power response of tunable lasers, like white lasers or titanium sapphire lasers for multiphoton, at a defined power, at 100%. And by varying the laser wavelength, it is possible to determine the characteristic power response curve of the tunable laser. Finally, it is also possible to measure the warm-up time of our lasers by starting a mid-time stability measurement immediately after switching on the laser and not after the recommended 1 hour. This work is a collaborative work for the GT3M Metrology Working Group, supported by CNRS and the French RTMFM network. You can find more details of the protocols and metrics at the Quarep-Limi Working Group 1 published protocol and the GT3M protocols by flashing these two QR codes. Thanks for watching and enjoy metrology.